So our first topic, our building theme for this unit is Lewis symbols. They're sometimes called Lewis dot diagrams or just dot diagrams. To write these, we start with the atomic symbol, and we're going to surround the atomic symbol by the number of valence electrons. Now, Lewis symbols is only done for representative elements. So that's group 1 and 2, and then group 3A all the way to 8A. Okay? Lewis symbols don't work for our transition metals or our D block. Lewis symbols are based on 8 valence electrons. And what you're told in Science 10 that there's 2, 8, 8 in the energy levels. Okay, so D is ignored. Okay. Another thing that's done in Lewis symbols is all of the orbitals are treated as having the same energy, and we'll dive into hybrid orbitals in our 4th lesson. So what that would look like if we think of there being, you know, the first energy level in the second or the third period would be an S, and then there'd be 3 P's. But we find out that some things happen when electrons are shared. The orbitals get mixed, okay? And Lewis symbols treats all those orbitals as put together in equal energy. So 4 equal orbitals, okay? 1 S and 3 P's are all mixed. And this is the heart of the 8 electrons that in Science 10 you're told to put in each energy level. Okay? For most representative atoms, this is all we need. And that's the starting point of that lie or that generalization. Okay? So let's look at some Lewis symbols. I'll start with lithium. Okay? So we put the atomic symbol in the middle. We write the valence electrons as dots around it. I'm going to write boxes in once and only once. Those 4 hybrid orbitals we treat as the top, the right, the bottom, and the left. Now we don't need to count total electrons, we just need the groups. Everything in group 1 has 1 valence electron. So lithium would have 1 dot in its Lewis dot diagram. Okay, so I'm going to draw that a little more cleanly. There's lithium with 1 dot. Going to move over a couple to boron. Boron is in group 3A, and everything in the 3rd group has 3 valence electrons. The outer energy level has 3. So I'm going to go 1, 2, 3. We spread out the electrons and we only pair them up when we have more than 4. Moving on to group 4A, carbon. It's the 4th group. So I go 1, 2, 3, 4. Okay. We're not filling up the S and moving on to the P's. We've mixed them all and we're just spreading them out before we pair up. When we get to oxygen, group 6A, we finally have to start pairing. 1, 2, 3, 4, 5, and 6. Now it doesn't matter where you put the pairs and where you put the singles. Most textbooks, teachers will start at the top, but that's not a rule. It's just how you're going to see this presented most of the time in teaching or books. What's really important is that we know that there are 2 pairs and 2 singles. And when we get into covalent bonding, sharing electrons, in something like water, we know that oxygen has 2 singles. And that's going to lead to the 2 bonds that oxygen's going to form. Last, when we get to a noble gas like neon, it's group 8A and has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay. The 4 pairs are all filled up. Neon is nice and stable. it has a full outer energy level. It doesn't have any single electrons that it wants to pair up to stabilize itself. Atoms want to have full energy levels. When there are unpaired electrons, that is quite unstable. It makes them reactive. So they either need to get rid of all the electrons so the outer energy level is totally empty and the next inner one is filled, or it needs to fill up those empty boxes. So most of our representative elements will want to have 8. The one exception we have to watch out for, remember, is our period 1s. The first energy level only holds 2 electrons. So the second, the third, the fourth of the representative elements all want to have 8 in its outer energy level, but hydrogen and helium is different. Hydrogen's Lewis symbol just has 1 dot, and we can't put 4 dots around hydrogen. You can only put 2 or 1 pair. If we move over to helium, we're not going to spread them out because that first energy level can only hold 2. Okay. So helium, we're going to put 2 dots together. Okay. So most representative atoms want to have 8, but hydrogen only can have 2, helium can only have 2. Okay. So that's going to be our basis. We're going to go into some bonding theory that's going to work for all of our types of bonding. The 2 main being ionic and covalent, okay? But bond theory is going to apply to both. Ionic, pluses and minuses, covalent is sharing. Okay. The first tenet of bond theory is that it's only valence electrons that are involved in bonding. So that's why Lewis symbols ignore the cores and just show the outer electrons. Okay. Those valence electrons, we can call them bonding electrons. Okay. We're going to discuss a few ways that atoms can get stabilized by having full outer energy levels. And there's 3 possibilities. So the first of 3 options to stabilize themselves would be to lose all their valence electrons. Okay. Then you're not going to see something with 7 electrons losing them all, okay. But you might see something like lithium with only 1 valence electron. It could lose that 1 electron and become a lithium plus ion, no dots, because it lost that 1 dot. Things with very low ionization energy, this is probably going to be the easiest thing they can do to get a full outer energy level. Okay. So losing all their electrons would make cations, positive ions. Okay. Some other elements will kind of do the opposite. Maybe they're only short 1 to have a full outer energy level, and they could gain that missing electron. So fluorine is in group 7, or 7A, with 7 valence. 1, 2, 3, 4, 5, 6, 7. Okay. To stabilize itself, it could pick up the 8th. It could gain 1 more electron, which I've made green, and become fluoride. Now, when we write Lewis symbols, we show all the dots. And there'll be a little bit more I'll add into Lewis symbols of ions in this lesson. Okay. The main theme here is we're making anions. So some atoms get stabilized by becoming a cation or anion, and this would be the heart of our ionic bonding, making two ions. What you haven't experienced much yet is the sharing of electrons to fill the outer energy level. And this will be our theme of the second, the third, the fourth, the fifth, and the sixth lesson. Okay? Sharing electrons, what's the structure, what's the bond angles. Okay? So this is new. Okay. A hydrogen atom with one single electron is missing one more electron. It could not lose it or gain it, but it could share a single electron from two different hydrogen atoms could pair up, okay, and share one each so that they have a pair. And when they share, we tend to draw the pairs right in between. Each hydrogen atom can have two electrons, but it doesn't own two. It's sharing the two. And again, that's covalent. Okay. For the first 20 elements, and in particular, pretty much all the representative elements, okay, they want to fill s and p orbitals, so they want to have 8 electrons. So both in high school and post-secondary, you'll hear the octet rule. Okay. Both ionic compounds and these new molecular compounds want to have 8 electrons around them. They don't have to own all 8. They could have 4 and share another 4, and that would give them 8. Again, we saw 2 exceptions to this. Hydrogen and helium only want to have 2 because they're in the first energy level. Okay. The octet rule ignores the D block, transition metals. So we're going to talk a little bit about ionic bonding next and drawing Lewis symbols for ions. Okay, we saw Lewis symbols for neutral species on our opening slide. Okay, we're going to start adding and removing some dots. Okay. So our one slide on ionic bonding. So ionic bonding is an electrostatic, so positives and negatives, cations and anions, okay, between low ionization energy atoms, so like group 1, group 2, okay, and more, but that's the heart of it, our metals and high electron affinity atoms, those would be our non-metals, in particular group 7. So group 1 and group 7 would be the biggest extreme here for low ionization energy and high electron affinity. I'm going to do an example with a group 2 and a group 6. You see a metal and a non-metal and you think science 10 and you should be thinking ionic bonding. But it fits with the ionization energy and electron affinity that we talked about previously. So first I'm going to do the reaction, and then I'm going to do the electron dot representation of this reaction. Okay. So calcium can react with oxygen. Okay. We're going to get an ionic compound. Okay. So the calcium will form an ion, oxygen will form an ion. We're going to have to think of what charges they would have and have a nice neutral formula unit. Now, all ionic compounds are soluble, are solids. They have really high melting points. Hopefully you did a lab last year where you tested melting points of ionic compounds. So I'm using pure science 10 here. Calcium, what charge would it have in a ionic compound? You'd look at the group or your data table. Everything in group 2 is +2 when it's an ion. And that's right in your Alberta formula sheet. Oxygen doesn't have the charge written in. Oxygen in group 6 is 2 away from a noble gas. It needs 2 electrons to be like a noble gas. It's going to have a -2 charge. So we're going to have a positive 2 cation, a negative 2 anion, that balances each other. So we don't need any subscripts. Okay. So that is balanced. I've predicted the correct product. I just need to balance this whole chemical reaction. 1 calcium, 2 O's at the beginning. So I need 2 O's at the end. So I just double that formula unit. That doubled my calcium. I can fix that. So that's not the new part. That's the old bonding, predicting the charges. Let's look at this new electron dot or Lewis symbol representation. Okay, I'm not doing a balanced equation now. I'm just doing a symbol to represent one of the species above it. Okay, so how can we think of calcium? Okay, the Lewis symbol for calcium is Ca. It is in group 2. So as a neutral atom, it would have 2 valence electrons, which gives us a visual. That's why it becomes a +2 ion when it loses those 2 blue dots. Okay, 1 oxygen atom. I know that says O2, but I'm just drawing 1 oxygen. 1, 2, 3, 4, 5, 6. Okay. Oxygen has 2 singles. Okay. There are 2 sort of boxes or orbitals that are missing an electron. Okay. Well, oxygen needs 2, calcium's got 2 extra, and there's going to be a transfer from the calcium to the oxygen. Okay. So now, what do the Lewis symbols look like for our products? We've got calcium, Ca, and Lewis symbols would show dots. How many dots are left in the calcium ion? Not a very big number. It is 0. The 2 blue dots have been lost. Okay. Now we still have to, when something has a charge, we have to write in the charge, but there's no dots. Okay. Whenever something has a charge, the rules say you have to put in square brackets. Okay. That's how the chemistry governing bodies say you do Lewis symbols for ions. You put the symbol, you put any dots you should have. Sometimes it's none. You put square brackets, you put the charge outside. So the ions have way more steps, nuances than the atoms do. Okay. Let's do the same thing for oxygen. Now, how many dots does the oxygen 2- have? Well, it had 6 from the beginning, but then it's gained 2 more to get 8 and be stable. So it's got 1, 2, 3, 4, 5, 6 that it had before. The answer doesn't have to color code them, but I'm color coding them for emphasis. The 7th and the 8th, taken from calcium. Now we have to square bracket the symbol O and its dots, have the charge outside. So those are the Lewis symbols for the 2 ions that we made. Okay. Calcium, no dots. Oxygen, 8. You're going to find the cations always have no dots. The anions always have 8, a full outer energy level. I'll do this once more. When lithium and nitrogen react. I'm going to do this one a little bit quicker. Okay. So we've got a group 1 and a group 6, a metal and a non-metal. We're going to get lithium plus. Okay. I'm not doing the Lewis symbols yet. I'm just doing kind of the science 10, predicting the product. Okay. It's going to pair up with nitrogen, okay, just one of those ends, and nitrogen is in group 5. Sorry, I think I said group 6 by mistake before. Group 5, it's 3-. Group 5, it gains the 6th, the 7th, and the 8th, 3 electrons. Well, +1 and 3- don't balance each other. You're going to need 3 lithium ions to balance the nitride. And then this is a little tricky to balance. We have to have the same count on each side. To balance the nitrogen, there's 2 at the beginning, so I have to have 2 formula units of that lithium nitride. That balances my N. I now have 6 lithium, so I need to have, at the end, I need to have 6 at the beginning. That's not the heart of what we're trying to do. It's drawing Lewis symbols. So every one of those 6 lithium, those are neutral. Okay? There is no charge written at the end of lithium. We don't write in zeros. Okay? So that has its electron. It's in group 1. We have nitrogen. There's no charge. Those aren't ions. Those are neutral. 1, 2, 3, 4, 5, because nitrogen, the nitrogen atom, is in group 5. Now I want to represent the Lewis symbol for the ions. So I'm going to do the order a little different. I'm going to put the square brackets in right away because all the ions need to have square brackets. I want to put the charge in right away. It's lithium plus. And how many dots does it have? That's none. Cations never have any dots. Lithium lost its 1 electron. Move on to the nitrogen. Again, I'm going to put the square bracket in right away because it's got a charge. How many dots does it have? Well, the atom had 5. And then it needs 3 more, which is why we needed that 3 lithiums. Each lithium can only give 1. So the first lithium will make a pair there, the second lithium a pair there, and the last lithium will pair up the last single black dot. And we get 8 with our nitrogen. Lithium emptied the outer energy level, so the next inner one is filled. So that's Lewis symbols for lithium nitride. A couple pictures, you've probably seen these before. This next slide, you're not meant to write these down, but I really want to emphasize, I don't want any student ever leaving my class thinking an ionic compound like sodium chloride has 1 sodium and 1 chloride and that's it. Okay? It is a repeating pattern. For every positive sodium, there is a negative chlorine, and we get a nice repeating 3-dimensional structure, okay, which we see here. We see this repeating pattern, this 1-to-1 ratio, okay, and then they flip. Okay. Around every green ball are a bunch of purple balls, opposite charges next to each other. Okay. Same diagram, it's just labeled differently and color-coded. For every sodium, there's a chloride. But if we look at a sodium in the middle, there's a chloride above it, to the left, to the right, to the bottom. If you look at a chloride, it's got the same sodium above, below, right, left in a 1-to-1 ratio. Okay? It's a repeating pattern. For every sodium ion, there is a chloride ion, and it repeats. Now, these charges give rise to the properties that were talked about last year, which I'm going to repeat a couple of them. Okay? Ionic compounds are very brittle. If you don't have the plus and minuses lined up holding it together, it'll snap. So if you hit an ionic compound and you force it to move over a little bit, and you get the minuses next to the minuses, it just shears off and breaks. Okay? And they also have very high melting points, often greater than 1,000 degrees Celsius. There are some in the 800s, but most are in excess of 1,000. It takes a lot of energy to get the positives and the negatives to separate from each other and flow like a liquid. And they also tend to be quite soluble. You put them in water and you can get the positives and negatives to come apart. So that's ionic bonding. Okay. We're going to make one extra prediction this year that we didn't make last year with ionic compounds. You can make a relative prediction about this melting point if you know something about the charge and you know something about the size. So that's what we're going to end with today. Okay. We're going to predict lattice energies, really melting points. Okay. Lattice energy, how much energy is in that positive, negative repeating pattern? If you know how much energy is in it, you can know how much temperature or thermal energy you need to sort of break it apart or pull them apart or separate them a little bit. So we have a relationship for lattice energy, but we care about relating it to melting points. And Coulomb's law is what we're going to use to make some melting point predictions. The energy is proportional to, that's that symbol next to the E, the positive charge, the negative charge, divided by the radius that those two charges are from each other. So that Q, you're not used to it, that is charge. So on the top, all we have is the charge of the cations and the charge of the anions. I used a little plus for the positives, cations, and the negative. So the numerator is saying the more charge you have, that's on the top, okay, the greater the energy, the lattice energy, or what we care about, the energy needed to melt it. Okay? So if ions have more charges, they'll have a higher melting point. Okay? So two ions that are +3 and -3 will have, everything else being equal, a higher melting point than a +1 and a -1. That's all we're trying to get out of that numerator. Okay? Or two +2s have a higher melting point than two -2s if the radius is the same. So we could look at charge differences to help predict melting points, or the radius is the distance between the cations and the anions. Okay? So that's really just the size. Okay? If they're bigger in size, larger radiuses, okay, they're further apart, that's a denominator. So a bigger size leads to a lower lattice energy and a lower melting point. Okay? The size is just going to come from our energy levels. Okay? If the valence electrons are in the second energy level, it's going to be relatively small compared to something that's in the sixth, has valence electrons in the sixth energy level. That'll be relatively big. So there's two things we need to look at. How big is the atom? What energy levels are being filled? And what are the charges? Let's take a look and end with sort of two examples. All your examples will have one of those two parameters being a controlled variable and the other being the manipulated variable. So that's what we got to figure out between sodium fluoride, sodium chloride, and sodium bromide. Okay. Is there charges changing here, or is there size changing? So sodium chloride would be Na plus F minus. Sodium's in group 1, fluoride in group 7. Sodium chloride, well, we got sodium again and Cl minus. And last, we have sodium bromide. And to make some predictions, we want to look at charge, differences, and size. More charges, higher melting points. Smaller size, higher melting points. Because the charges are close together. Okay. Is there a difference here in the charges between sodium fluoride, sodium chloride, and sodium bromide? No. Okay. So in this case study, the charges are a tie. Okay. So it's not the numerator that's going to determine the difference. We've got to look at a size difference. Well, the sodium is the same ion in all three examples. So we don't care about the sodium part. We've got to look at the anion. We've got fluorine or fluoride with 2 energy levels, chloride with 3, and bromide with 4. So I'm just using its position in the table to get the energy levels. So fluorine has electrons in the second, chlorine the third, bromine in the fourth. Okay? And the ions have just become like their noble gases, neon, argon, krypton. Okay? So what's going on here? This is the smallest. Bromide would be the largest. Sodium to bromide would be much further apart than sodium to fluoride would be much closer. Okay. And the sodium chloride in labels in the middle. So far apart, you can get those to melt easier. It doesn't take as much energy to separate things that are far apart to melt them. If they're really close together, it's going to take more energy to get the positives and the negatives apart. You just think of magnets. If magnets are far apart, you can pull them apart fairly easily. But if 2 magnets are right against each other, low distance, it takes more energy to pull them apart. Okay? Now, magnets are magnetic, not electric, but it's a nice comparison. Okay? So I'm not saying magnets are positives and negatives. It's an analogy. Okay? So the smallest would have the greatest melting point, and the sodium bromide would have the largest, smallest. So greatest is correct. So far apart, you can bring them apart. Okay? And that's all we're going to do with Coulomb's law. Make some predictions, compare things. One more case study to end today. Just 2 in this case study. Okay? Sodium chloride versus magnesium chloride. Sodium chloride, we kind of had from above, group 1 with a group 7A, a +1 cation and a -1 anion, versus magnesium. That's a group 2. That's a 2+ ion with chloride. So we need 2 of those chlorides. I'm going to make my list again. We have charge and we have size. Okay. Well, clearly the charge is not a tie here. We've got a +1 and a -1 versus a +2 and a -2. Magnesium has double the charge. Okay. So there is more charge here. Okay. I think of the first one would be a 1 and a 1. So if you try to create a scale, 1 times 1 is 1. For the magnesium chloride, we got 2 times 1. So charge is not the same. Would want to focus there. What about the size? So let's see. Sodium is in group 3. Period 3. So 3 energy levels. Chloride's in group 3. And magnesium is also in group 3. Everything is in the 3rd energy level. Similar size, not identical. You learned some trends, but the size is similar. There's no energy level difference there. So we're not going to focus in on that denominator, the size. We're going to focus in on the numerator, the charge. More charge, higher melting point. So our more charge is the second option. So we would expect a greater melting charge with the more greater melting point with magnesium chloride, a lower melting point with the sodium chloride. And that's how we can use Coulomb's law to make some melting point comparisons, okay? Non-numerical comparisons. So that's everything ionic, probably for high school. You're not going to learn anything new really about ionics next year. So we're going to practice this a bit and then move on to the new world of molecules next lesson.